Yasmin and I am going to present you satellite link budget. My other group member is Mahin Khushbakht Atiq. The outline of our presentation will be as follows. First of all, we will discuss link budget, its definition and equation. Then we will describe significance of calculating link budget, then design of communication links, then method of calculating link budget, design of downlink, direct broadcast TV link budget, design of downlink, design of uplink, and then references. Coming towards link budget. A link budget is actually simple addition and subtraction of gains and losses within an RF link. When these gains and losses of various components are determined and summed, the result is an estimation of end-to-end system performance in the real world. In other words, we can say a link budget is the accounting of all of the gains and losses from the transmitter through the medium to the receiver in a telecommunication system. It accounts for the attenuation of the transmitted signal due to propagation as well as the antenna gains, feed line and miscellaneous losses. Randomly varying channel gains such as fading are taken into account by adding some margin depending on the anticipated severity of its effects. The amount of margin required can be reduced by the use of mitigating techniques such as antenna diversity or frequency hopping. Coming towards link budget equation. A simple link budget equation looks like this. Received power in dBm is equals to transmitted power in dBm plus gains in dB minus losses in dB. Coming towards significance of link budget analysis. Link budget analysis is an important part of satellite communications to ensure a feasible and successful implementation of the satellite communication link. Due to the high cost of both space segment and ground station equipment, it is imperative that satellite communication links are carefully designed to optimize as well as safeguard the available resources. Design of satellite communication links is based on two objectives: meeting a minimum carrier to noise ratio for a specified percentage of time and carrying the maximum revenue earning traffic at minimum cost. Art of good system design is to reach the best compromise of system parameters that meets the specification at the lowest cost. Link budget is a tabular method of evaluating the received power and noise power in a radio link. It is impossible to design satellite link at the first attempt, so link budgets make the task easier because once a link budget has been established, it is easy to change any parameter and recalculate the result. Link budgets are usually calculated for a worst case when link will have lowest carrier to noise ratio. Factors which contribute to a worst case scenario include an earth station located at edge of satellite coverage zone where the received signal is 3 dB lower than in the center of the zone. Maximum path length from satellite to earth station. Low elevation angle at earth station giving highest atmospheric path attenuation. Maximum rain attenuation on link causing loss of received power and an increase in receiving system noise temperature. Earth station antennas are assumed to point it directly at the satellite, operating at their on-axis gain. If antenna is mispointed, a loss factor is included in the link budget to account for reduction in the antenna gain. Calculation of carrier to noise ratio in a satellite link is based on two equations for received signal path and received noise path. General equation is PR is equals to EIRP plus GR minus LP minus LA minus LTA minus LRA in dBW, where LP stands for path loss, LA stands for attenuation in atmosphere, LTA stands for losses associated with transmitting antenna, and LRA stands for losses associated with receiving antenna. Receiving system noise power is given by N is equals to K plus Ts plus Bn in dBW, where K is Boltzmann constant whose value is negative 228.6 dB watt per Kelvin per Hertz. Ts stands for system noise temperature in dB Kelvin and Bn is equals to noise bandwidth of receiver in dB Hertz. Now my other group member Mahin will take you further through the presentation.
Assalamu alaikum, this is Mahin. I would be discussing method of calculating link budget. We would first discuss the carrier to noise ratio for a single radio link, either downlink or uplink. Later, it would be demonstrated to do evaluation of carrier to noise for a complete satellite communication system. For example, in a two-way communication link, there will be 4 separate links, each requiring a calculation of channel to noise ratio. Design of downlinks. For downlinks, carrier to noise ratio is calculated in both clear sky and rain conditions, as all satellite communication is affected by rain attenuation. In a 6 to 4 GHz band, the effect of rain on the link is small, while in the 1411 GHz Ku band and 3020 GHz Ka band, rain attenuation becomes significant. Satellite links are designed to achieve reliabilities of 99.5 to 99.99% averaged over a year. Carrier to noise ratio in the receiver will fall below minimum permissible value for proper operation of link for between 0.5 and 0.01% of the year. This is called link outage. C bands are designed to have 99.99% reliability, that is 52 minutes outage, because rain attenuation rarely exceeds 1 or 2 dB. Outage times of 0.1 to 0.5% of the year, that is 8 to 40 hours, are usually tolerated for Ka band links. Allowable outage time also depends on type of traffic carried. Direct broadcast TV link budget design of downlink. Calculate the downlink link budget for Ku band DBS TV receiver when the transponder output power is 160 watt and the receiver is located on 3 dB contour of the satellite antenna beam. The satellite antenna gain is 34.3 dB and the receiving antenna gain is 33.5 dB. The link is operational at 12.2 GHz having path length of 38,000 km. Miscellaneous losses of 0.4 dB for the clear sky attenuation and 0.4 dB for the receiver antenna mispointing are allowed. At receiver antenna noise temperature is set to 35 Kelvin in clear sky conditions and a 12 GHz LNA with 110 Kelvin noise temperature is used. The system uses QPSK implementation whereby a QPSK signal with a symbol rate of 20 megasymbols per second is assumed. The threshold channel to noise value is set to 8.60. Coming towards the design of uplink. The uplink design is much easier than the downlink design in many cases. An accurately specified carrier power must be presented at the satellite transponder. Use of high power transmitters at earth station is possible. VSATs and satellite telephone systems, however, have low transmit powers. Satellite transponder is a quasi-linear, very nearly linear amplifier, and the received carrier level determines the output level. The high power amplifier in transponder must be run with a back off to avoid intermodulation products appearing at the output. The amount of power to be backed off is determined by the uplink carrier power received at the spacecraft. Earth station transmitter power is set by the power level required at the input of the transponder. This can be done in two ways. First, achieving a specific flux density at the satellite. Second, achieving a specific power level at the input of the transponder. This way is adopted as it helps finding the uplink. Finding channel to noise for uplink. It is the channel to noise ratio in the transponder measured in noise bandwidth Bn of the bandpass filter in the IF stage of the earth station receiver for which the uplink signal is intended. It is important that the uplink carrier to noise ratio be calculated in the bandwidth of the receiver and not the bandwidth of the transponder. Noise power at the transponder input is represented by NXP, where NXP is equal to K plus TXP plus Bn. Power received at the input of the transponder is PXP, where PXP is equal to PT plus GT plus GR minus LP minus LUP, where PTGT is uplink earth station EIRP, and GR is the satellite antenna gain. LP is the path loss, and LUP accounts for all the uplink losses other than the path loss. Value of channel to noise up at the LNA of satellite receiver is given by channel to noise is equal to PRX minus NXP. Finding the earth station transmitter output power. When channel to noise ratio is specified or known, the required transmit power at the earth station can be found from the equation just seen in the previous slide. It can also be calculated from the output power of the transponder and the transponder gain when these parameters are known. That is, PRXP is equal to PSAT minus GXP minus PO0, where PSAT is the saturated power of the transponder in dBW and GXP is the gain of the transponder in dB and BO0 is the output backoff in dB. This value of PXP is used in the following equation to find PT, where PXP is equal to PT plus GT plus GR minus LP minus LUP. These are the sources from where we took help. Thank you for listening to us, and Allah Hafiz.